I'll be speaking about something that I've been doing the last 4 or 5 years, which I really like a lot. And of course, these are some of the collaborators I've been working on with, mostly from UTRC and some people from UPenn. And these are some of the publications which relates to what I'm going to talk, if you're curious to know more. So the starting point is graphs. So we've been using graphs for many different applications, moreover lately with all this network control system and networks in general. So social networks, sensor networks, even in robotics, people have been doing something that is like a topological representation of an environment, which is represented with a graph, where nodes represent rooms and edges, connections between rooms, transportation networks, and even in biology to capture how different species evolve, we use phylogenetic trees. So graphs are everywhere, and they are a very useful mathematical representation, and there are a lot of properties and theorems you can use to analyze them. The question is, are those enough? I mean, the problem is that graphs are, in general, one-dimensional representations. And sometimes you really have problems where one-dimensional representations are not sufficient to capture the real problem. So a classical example is, say that I have a sensor network, and this circle is a footprint of the sensor, and you have potential intersections between footprints, and you ask yourself, is this network monitoring the entire space? I didn't show here, but say that there is a space here which you want to monitor, and you could associate a graph to this problem, but of course you see immediately that it's not going to be enough. I mean, here you see that there is a hole where sensors are not monitoring the environment. And the first thing that you would like to do is to say, okay, there is a cycle here, so maybe cycles would be the right thing, but a cycle here would be here and as well here, but here you see that instead the area is monitored, so cycles are not a good way to do that. What you really would like to do is to fill in this area and say, well, that has been monitored, is completely covered. The edges are going to be the faces of that triangle, and so on and so forth. So generally what you call a zero simplex is a vertex, an edge, it's a one simplex, a triangle is a two simplex, a tetrahedra, which is filled, is a three simplex, and so on and so forth. So this is sort of a generalization of a graph, where now you are capturing something more than just pairwise connectivity, but you're looking at high-dimensional relations, if you will. Now, what do you do with this stuff? Well, you're doing some computation on this simplicial complex representation, and the most basic one is homology. Homology is pretty much counting or determining information about the holes of your simplicial complex. So if you have a simplicial complex here with a hole, as we had before, what it turns out is that you can compute some group structure on this simplicial complex whose dimension has some information about the simplicial complex. For example, the zero of homology is dimension, is the number of connected components. So in this case, we have a connected simplicial complex. It's one-dimensional homology, if you take the dimension, is the number of one-dimensional holes. So in this case, is this hole here. And if you keep going, you will have ways to compute volumes, how many empty volumes there are, and hyperdimensional volumes. So if I go back in our examples, if I use this as a representation of what this sensor network is doing, then you find that what you would like to do is that the coverage is satisfied, or you have coverage if this H1 is trivial, so has zero dimension. Of course, in this case, has dimension 1 because there is one hole here. And so you can see that in this context, a graph representation is probably not the most suitable, whereas a simplicial complex representation where you inherently capture volumes or high-dimensional information is probably the more useful one. So here, coverage is not achieved. So in this talk, I'll give you some insight about some application where I have applied some of these techniques. And so the first one is about coarse localization with qualitative data. So the idea here is that you have a vehicle or a sensor which is moving in a complex environment and is sensing his near neighbors, whatever he sees around it. And in particular, we assume that there are some landmarks. I just, for simplicity, assume that they are the corner of this building. And we assume that the sensor does not know where it is. We don't know where the landmarks are. And for now, we assume that the landmarks are unique. So whenever you see a landmark, you know that is that landmark, and it's the only one that appears. So just to show this in a cartoon, you see that the guy is moving around, taking some observations, and wherever there is something in his field of view, you will be able to detect it. Now, what you can do is represent this environment using the observations and compute what we call an observation complex. Now, every time that I will show these things, they look like that I know the geometry of the problem. It's only a convenient way to plot it, otherwise I should plot it in a messy way. But I don't know where the vertices in space are. So just imagine that is a sort of an adjacency matrix which represent the underlying graph and how the faces or the triangles are glued on the edges. So I don't know how it is embedded in space, but I plot always embedded as if I knew how it is embedded. So how do you build this one? So given an observation, there is an edge if two observations share at least one common landmark. So this means that these two observations probably share this landmark, probably more than that, but at least one landmark was seen from both observations. And a triangle, a two-simplex, is if at least one observation was seen from 3 observation points, and so on and so forth. You can do the opposite. You can build a complex from the landmarks. So in this case, 2 landmarks are connected by a 1-simplex if they were seen from at least one observation point, a triangle or a 2-simplex if 3 were seen at least from our observation point, and so on and so forth. So now I have 2 simplicial complexes here, and what it turns out is that these are the dual of each other. And not only, but it's possible to demonstrate that the landmark complex and the observation complex, given that you have enough observation and landmarks, they actually are a faithful representation of the underlying environment. Not only, but their geometric counterpart is homotopy equivalent. So this means that if there is a hole here, there will be a hole here. If this is connected, this will be connected. And if I were to look at higher dimensional relations, they will also have the same. So in this case, through this tour, there is this sort of building in between, which is sort of creating a hole, and this hole appear in these 2 complexes. And their geometric representation, which in this case would be something similar to this because everything is embedded, is also having the hole, which corresponds to something like here, a building. So what can you do with this? So the idea here was, there has been a lot of localization using access points and so on, which is extremely difficult because of path loss, multipath, and so on. So what we were looking at is something which instead looks more of a trend of for example, power transmission or time of arrival or things like that. So assume that you are downtown in a city and you're navigating around and you're building your observation complex, for example, using Wi-Fi hotspots. So the idea here is that if I am this side of the building, it's very unlikely that if there are access points on this side, I will detect them because there is a full building in between, which means that these 2 observation points most likely will not be connected by an edge because they do not share access point in common. Of course, it can happen, and I can tell you how to resolve that. But for now, let's just make this simple assumption that if I am on one side of the building, it's most likely that I will not be able to see. Actually, I will not be able to see anything on this side. So you get a simplicial complex representation where the holes in the simplicial complex actually are the buildings, and the buildings are the holes. So the question is, how can I use this to do something intelligent? So then the starting point is a vehicle in an unknown environment. So we don't know where it is. We don't know where the landmarks are. We assume that it has an IMU, so it can at least integrate and do that reckoning. We assume that we have a map, a geometric map, with the footprints of the buildings. So this is my metric information. And what I do is I navigate around the city and collect the SSID or Wi-Fi access point. So that generally is unique. And then you can build a topological map. So in this case, actually, I made it a little bit distorted just to emphasize the fact that I don't know how this is embedded in space. I don't have geometric information. I have only relational information, meaning that from this observation point and this observation point, I was actually detecting the same, at least one access point, which was in common, and so on and so forth. Not only, but I can also put a pseudometric on top of this, just to give a little bit more granularity. So I can actually count how many holes there are in a near neighborhood or a far neighborhood, where far and near is the number of hops on the underlying graphs. So for example, if I consider this, one hop would be pretty much considering this, there are no holes. Maybe two hops would start to encircle some of the hole here, and I would say, okay, there are two holes. And now I will just combine this information, so the whole counting, and the whole counting based on some pseudometric with the metric information to try to correlate this thing that has holes with these holes which have a metric. So it's kind of having a tissue with holes, and you're trying to find a way to put it on something which is hard, which is represented by this map. Of course, we're not attempting to do any super accurate localization here, because as you can imagine, counting holes will not give you exactly where you are, but the idea was, can you do something with this information? So we did actually some experiments. So we went downtown. At the time, this work was at UTRC. So we went down Hartford, and we collected a bunch of access point, just the access point SSID. And this one is the trace of the GPS. So this is pure GPS. As you can see, it messes a lot where there are big buildings because of the multi-path. And so without going into too many details, here is a small trace of some of the results. So we initialized the particle filter to be having particles on the road network, because that makes the most sense. And you can see if this plays. Yeah, codec unavailable. So it doesn't play. So I can show in my computer. So in practice, there is a triangle representing the vehicle, which is moving. And you will see at the very beginning, the particle filter correlates a lot with this part of the environment and a bit more on this part. And as I start to move around here, you will see a lot of particles sort of concentrating towards there. So showing that being able to use holes, it does actually help you to find your position. Of course, you can imagine if you have extremely symmetric cities, then everything will break down, because the number of holes that you see near and far is going to be the same from every possible position, so that is not going to help. But generally, this is not the case in practice, and so you get something that actually provides you some interesting way to localize. So I call this qualitative localization because we're using practically no metric information, just a map which is providing footprints of a city. Now the question that I raised before was, well, what if I'm on the one side of the building and I do range with something which is across the building. So then in practice, what I'm doing, if you go back to this picture, for example, I would destroy the topology of the problem, because if this node and this node shared some access points, then there would be an edge connecting these two, which now makes this hole split it in two, which is a problem, because if I'm somewhere around here, I should be able to count one hole, whereas now I would have two. You can imagine this to be crazy if there are many holes that are split in many, many different ways. So the idea is to use what is called persistence homology. And the idea here is very simple from a cartoon perspective. So let's consider epsilon be the radius of a ball around a point. And now I grow the balls as a function of epsilon. So at the beginning, I can compute what is the group representing connectivity. And as you can see here, at the very, very beginning, when epsilon is 0 or very small, I will have 5 connected components, which correspond to the 5 nodes that are there. There are no holes, there are no voids, and nothing else. So there are only 5 nodes. As I now increase the epsilon, at some point, edges will start to appear where intersections between balls occurs. So for example, at this scenario here, in this case, I have 2 intersections here, and another one here. And now suddenly, I have 2 connected components corresponding to this and this. Can grow this one a little bit more, and now suddenly I have 3 intersections happening here, so all the pairwise intersections, and I'm here, so I skipped one of this, and you can see that I have this corresponding to this 2 simplex and 1 simplex, so I still have 2 connected components. In between, there was a situation where there was a hole here in between, so you were forming something that looked like this, so this where this is not filled. So you still had 2 connected components, but now there was a hole appearing there. And here is another example where now you have all intersections. So you have the graph here corresponding to all the intersections. This is filled, but this is empty. So there is a hole there. And so this is represented by the fact that there is a hole here, and then you have 1 connected component. So, and as you let epsilon go for various different, you can build what is called a barcode. And this barcode represents, in practice, how the topology of this problem changes as a function of epsilon. And why is this interesting? It's interesting because if you can imagine that this connectivity or intersections between different balls is noisy, then this provides you a way to understand that noise. And in particular, what you can see is that, for example, there is a very long bar here. So it means that there is a long persisting hole that appears for very large values of epsilons. Means that, well, most likely, these data contain inherently a hole, because this one is a very long persistent hole. And you can see that there are some void that appears and then some point disappears, but they're not very long bars, so this is probably something that is just happening because of noise. So in practice, what you're saying is that long bar corresponds most likely to the inherent topology of your data. And you can make these claims more formally, computing some particular metric on these diagrams. But the idea is that long bars corresponds to things which are inherently topologically properties of your data. And so here is an example where, for example, you have buildings, and now you can have communication. So we have access points, a lot of them around. You can see that there are communication occurring all over the place. And so here you would have many, many holes that appear. But if you now, and you have something that is doing 8 here, and you can see that if you do the persistent homology as I showed, where now the persistent parameter is not the distance, but is the power, for example, the signal strength, then you can see that there are two bars which persist the longest, corresponding exactly to these two holes. So in practice, a way that you can reduce the effect of this ranging through a building is to leverage the power, which most likely will be very small when a signal passes through the entire building, building a persistent, completely persistent homology. And what is nice here is that you're not committing to thresholding. You are looking at all possible values of power that you receive, and you're looking at what is that remain or is the strongest. I don't know how I'm doing with time. 5 minutes. So this was one of the early application on how do you do qualitative localization using SSID, and the fact that you need more than a graph to be able to do something like that. The other application is completely different. So here I was looking at privacy, as everybody is doing these days. But we started, instead of jumping to what now is differential privacy, everybody is doing differential privacy, we started from the most basic privacy-preserving algorithm that is usually fairly common. So the idea is that you have a database, you have a bunch of data, and you want to release this data for analysis. And the data usually has something that is a unique identifier of a person, like the social security number or their name and last name. Then you have things which you need to be able to do the analysis, but they could be correlated with information, aside information out there, and that can be used to re-identify people. So these are called quasi-identifiers. And then there are information which needs to be not tampered with, not privatized, because that is the information I really need to do my statistics. So for example, I'd like to be interested what is the salary depending on what people have borrowed and got scholarship for. So very easy way to do this is the k-Anonymity. And the idea here is to try to anonymize the data in a way where an entry here is not any more unique, but you change it in a way that there are at least k entries which are the same or more. So I think I have an example, yes. So simpler example, I have age, zip code, salary. And if I, for example, now, instead of saying that there is someone that is 25, 22, 24, I put it in an interval and say there are 3 records, which has age, 22, 25, 22, 25. And then the zip code, you can see that is the same if I were to remove the last 2 digits. If I remove the last 2 digits, and it's 476 ***, and then age 22 to 25. So now suddenly 3 records here become 1 record there. And now suddenly there is not a single record that look like this, but there are now 3 or more that look like that. So now you're achieving 3 anonymity. Now, of course, k-Anonymity is well known not to be very, having very strong privacy guarantees, but in general, so privacy it's a tricky problem because it can be, in general, it's a trivial problem, right? If I want to maintain privacy, don't share anything or share garbage. The problem is that you want to compute a function on the data. And that is where the problem is. If you corrupt the data too much, you retain privacy, but then the function you compute is useless. Vice versa, if the data is too clear, then the function that you compute is great, but the data is going to be not private anymore. And so k-Anonymity, despite having issues in some cases where you can actually re-identify people, it is one of the best in terms of maintaining or not corrupting data too much. So any function that you're going to compute, any analytics you do in the data tend to be much better compared, for example, to differential privacy, which is instead it's much better if you want to maintain privacy, but may not be the best when you do computations on it. So what is the idea here? If you think about these tables, well, it's only representing points, and right now I'm focusing on something that is numerical. I'm not putting categorical information like labels, say gender, things like that. I'll say a couple of words on how do you do that. So let's keep this just numerical. So you have points in RD dimension, in D-dimensional, depending on how many records you have, or labels, columns. So you have points. And now, as anonymization process, I use the things that I used before, this epsilon. I start grow this epsilon. And for example, at some point, these two intersect. And I say, OK, now the red and the purple, I can put them into the same bucket. I can put in the same equivalence class. And I can achieve, I call this a anonymity 1 simplex. And so what you're now growing these balls is to try to find a way to come up with equivalent classes. Of course, as in every privacy, if you grow this ball too much, then everything gets clumped into one class, which is always possible. But as I said, that would be perfectly private, but useless from a data analytics perspective. So the question really is, how do you decide how to grow these balls? Of course, one thing that you need to be careful here is that you need to distinguish these two cases, because these are very important. So in this case, I have an intersection between three generalization, where epsilon is my generalization level. So I can put these three data points into one class. In this case, I have the same but not filled triangles. So I have an issue, because now these two could be in equivalent class, but not this. These two could be, but not this. This could be, but not this. So how I handle this? So this suggests that a good epsilon should provide you something that is always filled and never have a hole. Because if it has a hole, then I don't know what to do with this. And so in some sense, a good anonymity, which is an epsilon, is the one for which the homology tend to be trivial. So I'll give you an example. Go back to this example, simple example here. And now I do, again, my persistent homology, where I let epsilon change the growth of these balls. And I'm looking at how the homology changes as a function of this epsilon. So in the beginning, you can see, if you remember before, you're going to get a bunch of disconnected components corresponding to all the different data points. That is obviously not achieving any anonymity. And then at some point, things start to becoming connected. And this is the minimum epsilon for which at least edges are there. And so I can at least have a 2 anonymity. So you get a full understanding of how the anonymity changes as a function of your epsilon. You can reuse the same diagram if you now also consider the dimensions of H1, which corresponds to the holes. And now you can see that I'm looking at triangles. So I'm looking at 3 anonymity. I need to put 3 data points in one bucket. And of course, then we start from a radius which is larger. But now you need to be careful, because some of the triangles that are going to be formed will have holes corresponding to this. And I don't know how to treat that case. So I need to consider only things which are filled. And so I need to remove situations where this is not filled. So these are regimes of anonymization which do not provide 3 anonymity. And you can do this, again, for higher order, for 4 anonymity, and so on. Here, for example, in this example, the H2 corresponding to voids is always trivial, so you never get that issue. But you also need to be careful to the fact that sometimes you can create, again, if you want a 4 anonymity, in some sense, either you're lucky that you find tetrahedras, but if you have only 5, 6 here, either you find 2 tetrahedras which are filled, or you need to find that are all in one 5 simplex. So in this case, for example, never happened that these points come up to be 2 tetrahedras, 2, 3 simplexes. Actually, I need 4 anonymity, so I actually would need a higher dimensional one. So in practice, these are regimes where you cannot have anonymity, so you need to go from 0, 4 above to be ensured to have high dimensional simplexes all connected without holes. So what is nice about this is that right now, algorithm for doing so k-Anonymity is an NP-hard problem. And generally, there are very efficient algorithms to do that, but you don't have a way to understand the trade-offs. You need to define a k. Okay, let's pick 5 anonymity, and then you just go and search for a way to do that. Here you have a full range of, you have a way to understand how anonymity changes, and you don't need to do a computation for each of them. It's the same homology computation that is done. It's only reinterpreting the same data in a different way. You can do this also for categorical data, which I don't explain how, but generally what people do is that you, of course, if you have labels like the countries, what is the generalization rules? There is not a metric, there is not an epsilon anymore. So typically you as a user need to define the generalization rules and then search for a way to combine data in a way that you can achieve the k-Anonymity. So for example, you can clamp Portugal and Spain to West Europe, East Europe into Europe, and then the world. If you have gender, male, female, become a person. And so you're finding all these different ways to generalize your data. Of course, now you don't have an epsilon anymore, but you can still look at this simplicial complex as just relations, right? I have Portugal and Spain, and I put an edge if now I abstract them or generalize them as West Europe. And Portugal, Spain, Hungary, and Finland will be all in a 3 simplex if I call them Europe, and so on and so forth. So now I have what is called more of an abstract simplicial representation. The previous one was a geometric one because I had the underlying geometry, and here there is no geometry anymore. Now you need to rely on more complicated way to compute the persistent homology. It's called zigzag, and to be able to get similar result. There are approximations here, though, that you need to take. So I don't know if I went too fast, or I think that's even 5 minutes. So this is just a very quick overview of some of the things that have been working, still working, which I like a lot, which go beyond the use of graphs, but looking at high dimensional information sometimes for problems is more suitable than looking at graphs. Thanks.